Astronomers have just uncovered something so strange, so completely outside the bounds of what we consider normal, that many are struggling to wrap their minds around it. Right now, as you watch this, 7 comets, yes, 7, are racing toward the sun, each on a collision course with its perihelion, all arriving within days of one another in October 2025. In all of human history, nothing like this has ever been recorded. And as if that were not enough to rattle even the most seasoned scientist, there is another player on the cosmic stage, one that might just be the most unsettling of all. 3I Atlas, an interstellar visitor from beyond our solar system, is also making its closest approach during this very same window. The statistical odds of these two events overlapping are so small that many astronomers describe them as virtually zero, unless, of course, something or someone is coordinating them. This leads to the most provocative question of all. What if what we are witnessing is not a random coincidence, not a simple cosmic parade, but the first act of something far larger, far stranger, and perhaps far more dangerous? Tonight, we are going to follow this mystery wherever it leads. We will examine every possibility, from the most conservative to the most speculative, and try to understand what these synchronized arrivals might mean. Stay with us until the end, because we will explore what 3I Atlas could actually be doing to our solar system, and why 2025 may be remembered as the year the skies came alive. Let's begin with part 1, a sky filled with visitors. In a normal year, astronomers are lucky if they get one truly spectacular comet, maybe 2, if fortune smiles. Most years, the so-called cometary events are nothing more than faint smudges only visible through a telescope, thrilling only the most devoted comet hunters and astrophotographers. But 2025 is something else entirely. It is as if the universe decided to open the floodgates and give us a front row seat to the most elaborate cometary performance ever staged. Meet the lineup that has professional observatories, double-checking their data, and amateurs, staying up all night with cameras pointed skyward. Pan-STARRS, SWAN, Stereo, Atlas K1, Atlas G3, Lemon, and NEAT. 7 distinct icy travelers, each originating from the far reaches of our solar system's Oort cloud, all descending toward the sun in near synchrony, like guests arriving fashionably late to a cosmic gala. To understand how bizarre this is, imagine you live alone and 7 of your friends from across the country all show up unannounced at your door. Not on the same day, not even the same week, but on the very same weekend. Possible, sure, coincidence, perhaps. But wouldn't you start to wonder whether someone sent out invitations behind your back? That is exactly the kind of suspicion many astronomers feel as they watch these 7 comets cluster together in their arrival times. In fact, astronomers have a name for this phenomenon. They call it a swarm event. When multiple comets arrive within a short observational window, it creates a pattern that looks, from Earth's perspective, almost orchestrated. Instead of a random sprinkle of cometary appearances spread across years or decades, 2025 gives us a tightly packed cluster, so visually striking that the pattern leaps off the charts. Normally, comet arrival dates are plotted as scattered dots across time, like raindrops on pavement. This year, the chart looks like someone dumped a handful of marbles all at once. Photography forums are already buzzing. Social media is flooded with side-by-side images of multiple comet tails captured in the same frame. Time-lapse videos show what looks less like random celestial debris and more like a choreographed ballet across the heavens. The effect is eerie, beautiful, and deeply thought-provoking. But this is where our investigation takes a sharp turn into even stranger territory. Because while these 7 comets are remarkable enough on their own, they are not the only visitors passing through our solar system right now. There is another object out there, one with no family ties to our sun, no allegiance to its planets, an interstellar traveler named 3I Atlas. It is only the 3rd confirmed interstellar object ever observed in our cosmic neighborhood, after Oumuamua in 2017 and 2I Borisov in 2019. Unlike our homegrown comets, this one was forged around another star system entirely, likely millions of years ago, and it is passing through just this once, on a hyperbolic trajectory that will fling it back into interstellar space forever. The timing is what has scientists unsettled. The fact that our solar system's most unusually comet-rich year coincides with the brief visit of an interstellar wanderer has sparked countless late-night discussions among planetary scientists. astrophysicists and data analysts. Is this truly just a freakishly rare overlap of events, or is there something deliberate, something coordinated taking place? As we move forward with this investigation, let's be clear about one thing. We are going to separate hard evidence from speculation. When we present you with orbital elements, brightness measurements, and perihelion dates, you can trust that these numbers are taken directly from observation logs and peer-reviewed data. When we speculate, when we ask what if, we will mark it clearly so you know where the science ends and imagination begins. This is not about pushing conspiracy theories. It is about following the evidence to its logical limits and asking the questions that beg to be asked. Here's how we will approach this. If 3I Atlas is somehow connected to this swarm of 7 comets, that connection should not be a vague hunch or a poetic coincidence. It should leave a signature in the data. We are talking about correlations and timing that exceed statistical probability. We are talking about orbital relationships that suggest common perturbations. We are talking about measurable gravitational or electromagnetic influences that can be verified independently. Anything less would not convince the skeptical scientific community, because the stakes here are not small. If these comets are simply obeying the mathematics of Newtonian mechanics, then what we are seeing is an incredible but natural cosmic coincidence, nothing more. The universe is vast, and in a vast universe, unlikely events do happen. But if some force, gravitational, magnetic, or something beyond what we currently understand, has nudged these comets into a synchronized approach, then we are looking at evidence of a power operating on a scale that challenges our comprehension. Such a discovery would reshape our understanding of how objects move through space and how our solar system interacts with the larger galaxy. Remember, every orbit is a story. Every trajectory carries the fingerprints of the forces that shaped it. If something guided these 7 comets into their present alignments, those fingerprints should still be there, waiting to be found. And when we add 3I Atlas to the equation, the mystery deepens even further. This object is not just a lump of rock and ice. It carries with it material formed around another sun, scarred by cosmic radiation and ancient collisions, seasoned by eons of travel through the interstellar medium. Studying its composition could tell us how other planetary systems form, evolve, and die. Watching how it behaves near our sun could reveal how alien materials respond to stellar radiation. But what if its visit isn't simply a random detour through our neighborhood? What if it is part of a much larger chain of events, a gravitational cascade, a galactic alignment, or even an intentional signal? These are the questions that multiply like fractals, each answer branching into 10 more questions. Could there be a mechanism capable of coordinating objects across such vast distances? Could such a mechanism be natural, or would it have to be artificial, a product of intelligence? And if intelligence is involved, what is the message? What is the purpose? As we prepare to take a closer look at each of these 7 comets, their orbits, and the interstellar stranger threading its way through them, remember this: the universe rarely gives up its secrets easily. But when it does, it has a way of changing everything we thought we knew. Every discovery in the history of science begins with an observation that doesn't quite match the expected pattern. Every major breakthrough starts with someone asking, why does this not behave the way we thought it should? What we are witnessing right now is exactly that kind of moment. The swarm has arrived, 7 distinct comets, all converging on the inner solar system within the same short window. And with it come questions that may challenge everything we think we know about how our solar system works. Before we dive into the bigger implications, we must meet our 7 visitors properly, because each one has its own story to tell. Think of this as a celestial roll call, a kind of cosmic lineup where every suspect claims to have an alibi, but somehow, they all showed up at the same crime scene. Our first visitor takes center stage with style: comet Pan-STARRS, discovered by the Panoramic Survey Telescope and Rapid Response System in Hawaii, a state-of-the-art sky patrol that has revolutionized the detection of comets and near-Earth objects. Pan-STARRS is predicted to become one of the brightest comets of 2025. It could even reach naked-eye visibility for observers across the northern hemisphere. The observation window stretches from late March through May 2025, offering weeks, even months, of continuous study. But what makes Pan-STARRS particularly fascinating isn't just its brightness potential, it's the geometry of its orbit. Its path crosses close to Earth's orbital plane, which means it will be well positioned for observation from populated regions of our planet. To a mind that is looking for patterns, this seems almost too perfect, too convenient, for an object that supposedly wandered in from the distant Oort cloud purely by chance. Next on our list is Comet Swan, whose very method of discovery sets it apart. The solar wind anisotropies instrument, designed to study the flow of particles streaming off the sun, accidentally became one of astronomy's most productive comet detectors. Swan comets are often first seen not by optical telescopes but by their hydrogen emissions, which show up as glowing signatures against the solar wind. When astronomers first detected Swan this year, it was already actively releasing gas, which means it had likely been venting material for months, possibly even years. This tells us that Swan wasn't a dormant, frozen object suddenly awakened by solar heating. It was prepared, fully active, and already announcing itself long before we pointed optical instruments at it. For a supposedly random visitor, its timing feels almost deliberate, as if it wanted to be noticed. Then we have Stereo, perhaps the most dramatic entry in our lineup. This comet was detected by the Solar and Terrestrial Relations Observatory spacecraft, satellites whose primary mission is to monitor the sun's activity, not to hunt comets. Stereo comets are known for their daredevil behavior. They plunge close to the sun, often becoming spectacular sun grazers. Some disintegrate completely during their close pass, while others survive the encounter but are forever changed by the heat and gravitational stress. What makes Stereo's arrival especially noteworthy is its timing. It will pass the sun during a period of heightened solar activity, near the solar maximum, when the sun's magnetic field is at its most chaotic. Could this be a coincidence? Or does the solar cycle somehow play a role in drawing objects from the outer solar system inward? The connection is tantalizing and far too neat to dismiss out of hand. Our fourth comet is Atlas K1, the one that raised the most hype early on. When the Asteroid Terrestrial Impact Last Alert System first spotted it, brightness predictions suggested it might become one of the most spectacular comets in decades. Headlines called it a potential comet of the century. Reality, as usual, has been more modest. Atlas K1 will probably require binoculars or a small telescope for clear viewing. And yet, its presence in this lineup is suspicious. Its orbit has been stable for thousands of years, and yet we just happen to discover it now, right in the middle of this unprecedented swarm. Why are we seeing it this year? The very year 6 other comets happen to share the stage. Close behind comes Atlas G3, a sibling of K1, discovered by the same Hawaiian survey system. The Atlas survey is one of the most powerful tools we have for detecting objects that move against the fixed background of stars, scanning the entire visible sky every few nights. The fact that multiple members of this swarm were discovered by Atlas is not suspicious by itself. Atlas is simply that good at its job. But it does raise the question, why are so many comets appearing now, at this particular moment, for Atlas to find? It feels as if the sky itself has grown more crowded, as though something out there has stirred the quiet outskirts of the solar system and sent these travelers inward all at once. Comet Lemon is next on our roll call. Discovered by the Catalina Sky Survey team operating from Mount Lemmon Observatory in Arizona, the Catalina project has been running for decades and has cataloged thousands of asteroids and comets. Discoveries from this program are backed by a long history of precise observation and orbital calculation, which makes Lemon's presence all the more intriguing. On its own, Lemon might not turn many heads. It will likely be a binocular object at best. But its position in this cosmic lineup is suspiciously perfect. It arrives right in the middle of the group, neither leading the swarm nor trailing behind. Its timing almost feels like it is maintaining formation, as though this were some sort of synchronized march toward the sun. Finally, we have NEAT, the Near-Earth Asteroid Tracking Program's contribution to this bizarre parade. NEAT was shut down in 2007, but its discoveries live on, their orbits carefully tracked and refined over the years. NEAT's comet was always destined to arrive in 2025. There was no guesswork here, no chance finding. We knew where it would be and when for over a decade. And yet here it is, arriving alongside 6 companions right on time, as though answering a cosmic roll call. When astronomers plot all 7 of these cometary orbits on a single timeline, the pattern becomes impossible to ignore. These are not simply comets discovered in 2025 that happen to be visible now. They were discovered across different years, by different surveys using different techniques. Hydrogen emissions, solar monitoring spacecraft, asteroid search programs, and dedicated comet surveys. And yet, every one of them reaches perihelion within months of the others. The diversity of their discovery methods actually makes the coincidence more striking. It is as if the universe wanted to be sure we would notice this event. If one survey missed a clue, another would find it. If optical telescopes failed to catch a glimpse, a solar observatory would pick up the hydrogen signature. When you put all the data together, the clustering is statistically extraordinary. Comet discoveries typically follow a random distribution over time, with an occasional small cluster of 2 or 3 arrivals. 7 comets arriving in such a narrow window is a statistical outlier so extreme that it practically demands explanation. And this is where the mystery deepens. Each of these objects has been following its orbit for thousands, even millions of years. The paths were set long before humanity learned to look up and name the stars. If this clustering was not caused by chance, then something must have nudged these objects, some force acting across incomprehensible distances and timescales. No one is asserting outright that this is deliberate coordination, not yet. But when you step back and look at the entire pattern, it is hard not to feel as though there is some hidden connection binding these 7 visitors together. Whatever the explanation is, gravitational resonance, a distant passing star's influence, or something far stranger, the pattern is real, and it is worth investigating. Because while every single comet follows the perfectly natural and predictable laws of celestial mechanics, their collective behavior in 2025 seems to whisper of something beyond mere coincidence. It is not just that they are arriving, it is when and how many of them are arriving that strikes seasoned astronomers as uncanny. Before we even attempt to connect this flurry of cometary arrivals to our enigmatic interstellar visitor, we first need to understand what a normal year for comets actually looks like. Without that baseline, we risk mistaking natural variation for something more mysterious. This is why our investigation begins with an honest assessment. What does an ordinary comet year look like, and why does 2025 appear so unusual? Imagine walking into a planetarium on an average year and asking the astronomer on duty, "What comets can I see tonight?" They would likely give a tired smile, check their database, and perhaps mention one faint object visible only through a decent telescope under truly dark skies. If you were lucky, they might tell you about a comet just barely bright enough to glimpse through binoculars, a faint, ghostly smudge near some unremarkable star. Most years come and go without a single comet bright enough to be seen with the naked eye. This is the frustrating but accepted reality of comet watching. It is mostly an exercise in patience, perseverance, and learning to appreciate dim rewards. For amateur astronomers, this cycle of disappointment occasionally pays off with a brief spectacle. For the general public, however, comets might as well not exist at all. They live in history books, in medieval paintings of bad omens, and in disaster movies where they threaten civilization. Rarely do they enter ordinary life, but 2025 has broken this quiet rhythm with the subtlety of a hammer blow. 7 significant comets have arrived within months of each other, several bright enough for photography with ordinary consumer cameras, some easily visible through binoculars, and at least one on track to become a naked-eye spectacle. This level of clustering simply does not happen, or at least it has not happened in living memory. To appreciate just how remarkable this is, we need to explore the mathematics of comet discovery and visibility. Modern technology has made our surveys of the sky much more complete, but it has not changed the fundamental physics that governs when comets appear and how bright they get. The Pan-STARRS survey in Hawaii, for example, sweeps the entire sky every few nights, capturing faint moving objects against the background stars. The Catalina Sky Survey in Arizona systematically scans other regions of the sky, while space-based telescopes like NEOWISE and its successors detect the heat signatures of objects invisible to ground-based instruments. Collectively, these programs discover hundreds of new comets and asteroids each year, but discovery does not equal spectacle. The vast majority of these objects remain forever locked in the domain of professional astronomy, faint points of light whose only claim to fame is a catalog number. Only a tiny fraction of these bodies ever become bright enough to catch the eye of the public. Statistically, any given year produces 0 or 1 naked-eye comet, and perhaps 2 or 3 others that are just barely accessible to serious amateur observers. This is why 2025 feels so anomalous. Improved technology has indeed increased the number of discovered objects, but it has not increased the percentage of those objects that become bright and beautiful. Better telescopes do not make bright comets. They merely find more faint ones. A comet's brightness is determined by intrinsic characteristics that were set millions of years ago: its size, its composition, and the geometry of its closest approach to the Sun. The fact that so many bright comets happen to be arriving now is not a result of better sky surveys. It is a result of the cosmic dice roll that was cast long before humanity even existed. We are simply here at the right time to witness their arrival. This distinction is critical. If the surge of comets in 2025 were merely an artifact of improved detection, we would expect similar upticks in other recent years as telescope technology advanced. But the data show no such trend. Instead, 2025 stands out as a genuine, statistically unusual concentration of bright comets. Of course, we must be cautious. Media coverage has a habit of exaggerating even modest astronomical events. Headlines promising a comet of the century often lead to public disappointment when the object turns out to be a faint smear, barely visible even under dark skies. Astronomers therefore rely on a rigorous system for measuring brightness, the magnitude scale, which works in reverse, with smaller numbers meaning brighter objects. Magnitude 6 is roughly the limit of naked eye visibility under pristine skies far from city lights. Most suburban observers need magnitude 4 or brighter to see anything without optical aid. Predicting comet brightness is notoriously tricky because it depends on outgassing rates, which in turn depend on composition, solar heating, and rotational dynamics. Some comets flare dramatically when fresh ice is suddenly exposed, while others fizzle because their surfaces become coated in insulating dust that suppresses further activity. Still, experienced comet watchers develop good instincts for which objects are likely to perform. When veteran astronomers say that 2025's comet calendar is exceptional, their words carry weight. These are people who have spent decades tracking faint objects across empty star fields, patiently logging data on countless unremarkable comets. Their surprise tells us that something genuinely out of the ordinary is happening. Adding to the intrigue is the timing of this comet swarm with the solar cycle. Our Sun operates on an 11-year cycle of activity, alternating between solar minimum, a relatively calm period, and solar maximum, a stormier phase characterized by sunspots, flares, and coronal mass ejections. The year 2025 happens to coincide with solar maximum, meaning the Sun's magnetic field is at peak turbulence. This heightened activity can dramatically affect how comets look. Solar storms can rip off portions of comet tails, creating dramatic disconnection events. Enhanced solar wind also intensifies the ion tails of comets, making them more vivid and photogenic. In other words, solar maximum can enhance the spectacle, but it does not summon comets into existence. The bodies heading toward the inner solar system this year would be arriving whether the Sun was quiet or active. And yet, even after accounting for solar effects, the clustering feels too perfect. This is where psychology enters the story. Human brains are pattern recognition machines. Our ancestors survived by spotting faint patterns in animal tracks, in changing seasons, in the behavior of the wind. This tendency has served us well, but it also means we often see order where none exists. We look at a cluster of events and instinctively assume they are connected. When 7 unusual comets show up in a single year, it feels intentional, as though some cosmic hand arranged them for our benefit or our warning. But randomness produces clusters all the time. Flip a coin long enough and you will eventually see long runs of heads or tails that feel impossible, but are actually inevitable given enough trials. The challenge for scientists is separating genuine anomalies from mere statistical quirks that just look meaningful to our pattern-hungry brains. This is where orbital analysis becomes vital. If these 7 comets share similar source regions, orbital inclinations, or timing patterns that go beyond what chance would allow, then we may have evidence of some common cause, perhaps a gravitational perturbation in the distant past that sent them sunward together. On the other hand, if their orbits are widely scattered and unrelated, then coincidence remains the simplest explanation. And as astronomers often remind us, extraordinary claims require extraordinary evidence. The idea that some unseen force deliberately herded 7 comets into coordinated arrivals is indeed extraordinary. To convince skeptics, we would need clear, reproducible signatures, orbital elements that defy random distribution, perturbations that imply a common trigger, or some external agent capable of synchronizing such events across vast distances. And yet, history teaches humility. The universe has surprised us before, upending assumptions we thought unshakable. Sometimes the improbable explanation turns out to be true. Sometimes coincidences conceal deeper truths waiting to be uncovered. The swarm is not imaginary. The timing really is unusual. The questions it raises are profound. Could there be a deeper story unfolding? One that ties together these comets and the interstellar object now visiting our solar system? When astronomers encounter a mystery, they usually begin with two fundamental forces: gravity and electromagnetism. These two govern nearly everything that happens in space, from the orbits of planets to the graceful arcs of comet tails. If something truly is coordinating these 7 comets, it must be doing so through one of these mechanisms. Gravity is the obvious first candidate. It is the grand architect of the solar system, warping space-time around every object with mass and guiding planets and comets alike along predictable trajectories. Gravity acts across infinite distances with exquisite mathematical precision, allowing astronomers to forecast celestial events centuries or even millennia into the future. But gravity also has a limitation. It is incredibly weak. Only enormous masses, planets, stars, or perhaps dark matter structures, can produce effects significant enough to influence comets across interplanetary space. If gravity is responsible for this clustering, then something massive must have been at work in the distant past to send these objects sunward together. And this is where our investigation truly begins, with the search for that massive, perhaps invisible hand guiding these icy visitors on their synchronized journey toward the sun. The sun, with its overwhelming gravitational dominance, is the master architect of our solar system. Its immense mass shapes the broad patterns of planetary motion, dictating the paths of planets, asteroids, and comets with unyielding precision. Every object, from the largest gas giant to the tiniest fragment of interplanetary dust, dances to the tune of solar gravity. Among these dancers, Jupiter holds a special place. Though it is just 1,000th the mass of the Sun, it remains powerful enough to exert a noticeable gravitational pull on countless smaller objects. Its influence is not subtle. It has sculpted the asteroid belt, corralled Trojan asteroids to accompany its orbit, and redirected comets with slingshot-like encounters. The scale of this influence helps us understand the magnitude of force required to shepherd celestial objects. For any object to coordinate the arrivals of 7 separate comets, it would need to have mass on the scale of a major planet. This is not a case of faint, cumulative gravitational nudges playing out over millions of years. We are talking about gravitational power that would be immediately obvious to astronomers running orbital simulations. The mathematics do not allow for hidden players. A comet's orbital elements, its inclination, eccentricity, and timing, are like fingerprints of every gravitational influence it has ever experienced. These signatures cannot be hidden or disguised. If there were a massive, unknown object shepherding this collection of comets into a synchronized arrival, its fingerprints would stand out in the data. Jupiter itself provides the perfect example of how gravitational shepherding works in practice. Its gravitational reach has carved distinct gaps in the asteroid belt, where objects simply cannot maintain stable orbits. It has captured entire families of Trojan asteroids that remain trapped in its gravitational wells, eternally leading and trailing the giant planet. Astronomers have observed countless comets having their paths bent, redirected, or even ejected from the solar system after close encounters with Jupiter. These effects are not theoretical. They are measurable, predictable, and calculable. Using this as a template, we can say with confidence that if there were an undiscovered massive object coordinating 7 comets, we would see its signature in their orbits. We would find consistent orbital perturbations, shared gravitational imprints, or synchronized timing anomalies pointing to a common cause. The absence of such evidence effectively rules out gravitational coordination. If not gravity, could electromagnetic forces be at work? Comets are not inert ice balls, they are electrically active. As they approach the sun, solar radiation ionizes their gas clouds, causing them to carry electric charges. Charged particles interact with the solar wind, that constant stream of particles flowing outward from the sun, and they respond to magnetic fields. These interactions shape a comet's glowing ion tail, producing beautiful twists and bends, and sometimes even disconnecting tails entirely during solar storms. But electromagnetic forces operate very differently from gravity. They affect the tail of a comet, the glowing gas and dust streaming behind it, without meaningfully altering the solid nucleus's path through space. A comet's orbit remains stubbornly governed by gravity, following the same trajectory it would have followed even if its tail were stripped away completely. For electromagnetic fields to steer 7 comets into coordinated arrivals, the field strength would need to be unimaginably powerful, far beyond anything ever observed in our solar system. The energy required would be so vast that it would dwarf the sun's own output. We are speaking of magnetic field intensities that are only found in the extreme environments surrounding neutron stars or black holes, places where physics bends to unimaginable extremes. Moreover, such strong electromagnetic interactions would produce unmistakable signatures. Every major observatory on Earth and in orbit would detect the spectral fingerprints of these interactions immediately. We would see anomalous tail behavior, unnatural emissions, and other evidence that could not be hidden. The fact that no such signatures have been observed rules out electromagnetic steering as well. This brings us to the critical difference between speculation and science: the demand for evidence. Real shepherding, whether by gravity or by electromagnetic force, must leave behind an observable trail of clues. These clues must survive the scrutiny of mathematical modeling and rigorous peer review. We would expect to see shared orbital elements pointing toward common influences, perturbations that cannot be dismissed as random error, or timing relationships too precise to be explained by chance. So let us apply these criteria to our 7 comets: Pan-STARRS, Swan, Stereo, Atlas K1, Atlas G3, Lemon, and NEAT. Do they share the kinds of orbital similarities that would suggest they are being influenced by the same force? The answer, according to the data, is no. Each of these comets follows an orbit consistent with independent evolution. Their source regions are different, their orbital inclinations diverge, and their arrival timings do not suggest anything more than random statistical clustering. Pan-STARRS comes from a different direction than Swan. Stereo's sun-grazing path bears no resemblance to Atlas K1's distant trajectory. Lemon and NEAT trace their origins to different parts of the outer solar system entirely. If a hidden shepherd were truly coordinating their arrivals, we would see subtle correlations, shared nodes where their paths cross, consistent timing patterns or common perturbations indicating shared gravitational influence. Instead, what we see are 7 independent travelers, each following its own unique route through space, converging only in the sense that they all happen to brighten during the same general period. Their orbits tell the story of solitary journeys shaped by solar gravity and the occasional nudge from passing planets. This does not entirely eliminate the possibility of some subtle coordinating influence, but it does raise the bar of evidence very high. If there is something hurting these comets, it is doing so in a way that is almost invisible to our current instruments. The simpler, more likely explanation is statistical clustering, enhanced by the fact that our comet surveys are now far more sensitive and capable than they were in the past, detecting objects we might have missed decades ago. And yet, the appearance of 3I Atlas adds an element of intrigue that we cannot easily ignore. Unlike the 7 comets, Atlas is an interstellar object, traveling on a hyperbolic trajectory that marks it as a visitor from beyond the solar system. It is under no obligation to follow the gravitational patterns that govern local objects. Its very presence is a reminder that our solar system is not isolated, but connected to the broader galaxy. Could such a visitor, despite its small mass, have influenced the timing or behavior of traditional comets in some way we do not yet understand? The idea challenges conventional physics, but it is worth considering. The limitations of 3I Atlas as a potential shepherd are obvious. It is far too small to exert meaningful gravitational influence. Its passage through the solar system is fleeting, and its trajectory does not bring it near any of the 7 comets. Nevertheless, the timing coincidence is compelling for those who suspect deeper patterns in the universe. An interstellar visitor arriving during one of the most active comet years in recent memory feels like more than a simple roll of the cosmic dice. Perhaps Atlas is not the cause, but the clue. A cosmic indicator that we are passing through a region of space where cometary activity is naturally enhanced. Maybe interstellar visitors tend to arrive during periods when the outer solar system experiences gravitational stirring, sending more comets sunward. This is speculative but not impossible, and it reminds us that nature often hides subtle connections waiting to be uncovered. As we continue this investigation, it is worth remembering that many great scientific discoveries began with observations that did not fit existing models. What seems impossible today may simply be a phenomenon we do not yet have the tools to measure. Sometimes the universe whispers before it speaks clearly, and so we sound the alarm. Not an alarm of danger, but of curiosity. This is not a siren of doom, but a signal calling us to look closer. Think of it as a cosmic smoke detector, alerting us to something unusual happening in our celestial neighborhood. The year 2025 promises to be a remarkable one for skywatchers, with multiple bright comets appearing at once, creating a show that will inspire countless people to look up. Photographers will capture stunning time-lapse sequences of these objects racing across the heavens. Social media will be filled with breathtaking images, and public interest in astronomy may surge. These events carry no threat. Comets are fragile objects made of dust, ice, and organic material, falling apart under solar heating. Even their closest approaches remain far from Earth by astronomical standards, with pan-stars passing well beyond the Moon's orbit and others even farther. The true alarm comes from the human mind's natural tendency to seek patterns, a survival mechanism honed by evolution. When multiple rare events occur close together in time, we instinctively search for a common cause. That impulse has driven science forward for centuries. Modern humans still carry the same pattern-seeking instincts that kept our ancestors alive. Those instincts worked well when the patterns we needed to detect were rustling bushes or approaching predators, but they are less reliable when applied to the cosmos, where events play out on scales vastly beyond human intuition. When we see 7 comets arriving within the same general time frame, we can't help but wonder if something coordinated them. Who or what sent them? What kind of force could synchronize such precision across billions of kilometers of space? Why now, and why all together? These questions grow even more compelling when we add one more element: the presence of 3I Atlas, an interstellar visitor whose arrival seems almost too perfectly timed to be coincidence. The narrative practically writes itself. First comes an alien probe from beyond the stars, then a comet swarm follows as if summoned. Something unusual must be happening, something that demands our immediate attention. Social media magnifies this sense of drama. Its algorithms reward mystery and speculation because they drive engagement. A video claiming that the comet swarm is a sign of alien intervention or cosmic conspiracy is almost guaranteed to rack up more clicks than a careful, measured explanation of orbital mechanics and probability. The more mysterious the narrative, the more it spreads. And as the story spreads, it grows. What might have begun as a harmless observation soon becomes a viral sensation, amplified by our collective hunger for meaning in what otherwise seems like a random and indifferent universe. This is where the rule of scientific accountability becomes essential. Bold claims must survive rigorous testing against known physics and observed data. Speculation is allowed, even encouraged, but it must be clearly labeled as such and held to proper evidentiary standards. Entertainment value, no matter how high, does not justify presenting unfounded theories as established fact. We must maintain the crucial distinction between spectacle and causality. Just because something is beautiful does not mean it was coordinated. Just because something is dramatic does not mean it is artificial. Just because something is impressive does not mean it is threatening. The universe routinely produces breathtaking natural phenomena without requiring exotic explanations. Take the year 2025 as an example. This is a year of solar maximum, when the sun is at the peak of its 11-year activity cycle. Solar maximum brings frequent coronal mass ejections, more sunspots, and intense streams of high-speed solar wind. These space weather effects can dramatically shape comet tails. Under the right conditions, a comet's ion tail can stretch across enormous swaths of the sky, sometimes spanning multiple degrees. Magnetic storms can trigger disconnection events, making it appear as though a comet's tail has snapped off, only for a new one to form soon after. Such events are spectacular to watch, and in the era of global connectivity, they are spectacular to share. Photographers will post breathtaking time-lapse videos of multiple comets glowing and evolving together, creating the illusion that they are responding to some unseen cosmic command. Social media feeds will fill with images that seem to show synchronized tail movements, simultaneous outbursts, and coordinated brightening events. The temptation will be to assume control, to see a hidden conductor orchestrating a celestial symphony. But the reality is far more mundane and, in many ways, far more fascinating. Each comet is responding independently to the same shared solar environment. The apparent coordination is no more mysterious than 7 different weather vanes pointing in the same direction during a strong windstorm. It is synchronized response, not centralized control. This brings us to another question. Why does this unusual comet year coincide with the peak of solar activity? Is this just coincidence? Or could there be a deeper connection between solar cycles and the rate at which comets begin their inward journeys from the outer solar system? Could gravitational perturbations or electromagnetic effects associated with solar maximum slightly increase the number of comets nudged sunward? These are fascinating questions that move us into the realm of testable speculation. Solar activity is one of the most well-documented cycles in astronomy, and we have historical comet data stretching back centuries. If solar maximum genuinely enhances comet activity or merely increases the likelihood of comet discovery due to more intense sky watching, the correlation should be visible in the data, but we must also be vigilant against confirmation bias, the tendency to notice only the data that fits our preferred conclusions while ignoring the rest. When we see strange tail behavior, our first step should be to check for solar storm activity. When a comet brightens suddenly, we should first examine whether solar heating or volatile release explains it. When we notice orbital anomalies, we must check our measurements, look for known sources of gravitational perturbation, and only then consider the possibility of unknown influences. This disciplined approach does not diminish wonder. It enhances it. It ensures that the mysteries we hold on to are real mysteries, not illusions born of incomplete data or human wishfulness. The universe provides plenty of legitimate puzzles without our needing to invent new ones. The 7-comet clustering of 2025 is just such a puzzle. Statistical anomalies like this are rare enough that they deserve careful study. If we eventually conclude that this is nothing more than coincidence enhanced by modern survey sensitivity, that conclusion is still valuable because it helps refine our understanding of solar system dynamics. But if we find correlations that truly exceed chance, shared orbital nodes, synchronized timing relationships, or behavioral anomalies, then we may be on the verge of discovering a new aspect of how the solar system works. The presence of 3I Atlas adds an additional layer of intrigue. Interstellar objects are exceedingly rare. Only 2 confirmed examples preceded Atlas, making this the 3rd known case in recorded history. That means its timing is genuinely significant rather than merely interesting. We are not suggesting that Atlas caused or coordinated the comet swarm, but its coincidental arrival during this unusually active comet year cannot be ignored. Even if no direct causal link exists, the coincidence could reveal indirect connections, helping us uncover previously hidden aspects of solar system behavior. Accountability in science is not just about avoiding false alarms, it is also about not dismissing genuine signals out of hand. History is filled with examples of ideas that sounded absurd at first, but turned out to be correct. Continental drift, meteorite impacts, and the existence of other galaxies were all once controversial or ridiculed claims. The challenge is to remain appropriately skeptical while staying open to evidence that could overturn existing paradigms. We need rigorous standards for extraordinary claims, but we must also remain flexible enough to accept extraordinary evidence when it finally appears. As we prepare to study 3I Atlas in more detail, we must remember that many of the greatest discoveries in science began with someone noticing something that didn't fit, something that felt too strange to ignore. Sometimes the universe really is trying to teach us something new, and sometimes that lesson arrives disguised as coincidence. The comet swarm has given us its signal. Now it is up to us to respond, not with panic or premature conclusions, but with careful measurement, modeling, and analysis. Whatever answers await us, they will be revealed by evidence, not speculation. And so we turn to our prime suspect, the interstellar stranger. 3I Atlas is the 3rd confirmed interstellar object ever detected passing through our solar system, a true cosmic wanderer. It formed around another star billions of years ago and has spent untold eons traveling through interstellar space before intersecting our neighborhood on its one and only visit. This distinction is crucial. Every other comet we have discussed was born within the solar system, forged from the same primordial materials that created the planets and moons. 3I Atlas, by contrast, is alien in the most literal sense. Its ices and dust formed under conditions we can only imagine, in a stellar nursery far from our own. It is, in a way, like finding a message in a bottle that washed ashore after drifting across not an ocean, But the gulf between stars. The journey of 3I Atlas has likely taken millions of years, a slow, silent odyssey through the vast emptiness of interstellar space. During this unimaginable span, our visitor drifted through the near-perfect vacuum, enduring constant bombardment from cosmic radiation and accumulating chemical scars that tell the story of its ancient voyage. For all the intrigue surrounding its arrival, one crucial fact must be emphasized. 3I Atlas poses no collision threat to Earth. Its trajectory is not a harbinger of doom, but a celestial drive-by. It will sweep past the sun and planets on a hyperbolic path, a one-time visit before gravity flings it back into the depths of interstellar space, never to return. If this is a mission, it is a mission of observation, not invasion, if the word mission even applies to what might be nothing more than a wandering shard of ancient ice. The strange, comet-like behavior of 3I Atlas only deepens the mystery. Far from the sun, where temperatures should keep its surface ice locked in a solid state, the object has grown a visible coma and faint tail. By all conventional understanding, solar heating at such distances should not be powerful enough to drive this level of outgassing. Yet telescopic observations leave no doubt. Its fuzzy glowing halo and streaming tail mark it as active, not inert. This premature activity hints at unusual internal chemistry, perhaps a mixture of supervolatiles capable of sublimating at extremely low temperatures, or even an internal heat source releasing energy independently of solar radiation. Each possibility offers tantalizing clues about the birthplace of 3I Atlas, which formed around another star under conditions utterly alien to our own solar nursery. This is what makes interstellar visitors so scientifically valuable. Every observation we make of 3I Atlas is a direct sample from another planetary system. Its composition, its brightness variations, its exact orbital trajectory, all are pieces of data that expand our understanding of how stars and planets form elsewhere in the galaxy. Spectroscopic readings of its ices and dust grains tell us what molecules condensed in its home system. Precise astrometry tracks its path, revealing how interstellar dynamics shape its motion. Each photon we collect is irreplaceable, a fragment of a message from across the gulf between stars. Yet our documentary is not just about the science of interstellar chemistry. We are exploring a more provocative question. Could the arrival of 3I Atlas be somehow linked to the extraordinary timing of the 7 comet swarm currently gracing our solar system? At first glance, the overlap could be nothing more than chance. After all, comets and interstellar objects follow their own independent courses through space. But the coincidence is striking enough to demand careful examination rather than casual dismissal. If there is a genuine connection, we would expect it to reveal itself in measurable ways. Correlations between timing that exceeds statistical randomness, orbital patterns suggesting a shared influence, or unusual activity in the comets that cannot be explained by standard solar effects. The absence of such signatures would argue against any connection, reducing the overlap to an interesting but ultimately meaningless fluke. But if those correlations exist, they could point toward forces or interactions on scales that challenge our current understanding of celestial mechanics. The implications would be profound. If an interstellar object can somehow influence the behavior of solar system comets, that would suggest previously unknown interaction mechanisms, perhaps gravitational, electromagnetic, or something even more subtle, that link stellar systems in ways we have not yet imagined. Such a discovery would expand our view of the cosmos, hinting that stellar neighborhoods are more connected than the vastness of space implies. Even without invoking exotic physics, the timing alone justifies attention. Based on current surveys, interstellar objects likely pass through our solar system only once every decade or so. Their arrivals should be scattered randomly through time, unrelated to local events like comet clusters. Yet here we are, with 3I Atlas making its flyby during what is already one of the most active comet years in recent memory. Statistically speaking, the odds of these events coinciding are low. The rarer each event is individually, the more noteworthy their overlap becomes. Of course, we must remember that correlation does not equal causation. Just because two phenomena happen together does not mean one caused the other. Suspicious timing is not evidence, but it is reason enough to investigate thoroughly. If the universe is trying to tell us something about hidden relationships between interstellar wanderers and our local cometary population, we must be prepared to listen carefully and scientifically. Managing expectations is crucial as we proceed. While our 7 comets may become dazzling naked-eye spectacles under the influence of solar maximum, 3I Atlas will almost certainly remain a telescopic object throughout its visit. Its true importance lies not in public spectacle, but in the unprecedented scientific insights it offers. Around the globe, teams of professional and amateur astronomers are coordinating their observation schedules, combining data from multiple instruments to extract every possible detail from its brief appearance. This campaign represents not just a chance to learn about a single interstellar visitor, but also our best opportunity to search for meaningful links between 3I Atlas and the 7 comet swarm. If there are shared anomalies, synchronized changes in brightness, coordinated shifts in tail direction, or other unusual behaviors, they should become apparent through simultaneous monitoring of all 8 objects. The challenge, however, is separating real connections from patterns our brains are eager to impose on noisy data. Human perception is wired to detect patterns, even where none exist. This was an evolutionary advantage in a dangerous world where missing a predator could be fatal. But in science, it can lead to false positives, seeing connections where the universe is simply playing dice. That is why our investigation maintains strict discipline in distinguishing observation from interpretation. The raw measurements, orbital parameters, brightness curves, spectroscopic data are objective facts. When we begin to propose relationships between those facts, we must step into the realm of hypothesis testing, where skepticism is as essential as curiosity. The scientific method provides a framework for this balance. Statistical tests allow us to measure how likely it is that a correlation arose by chance. Independent replication ensures that any pattern survives scrutiny from multiple teams using different instruments and methodologies. Extraordinary claims require extraordinary evidence, and the suggestion that an interstellar object is influencing solar system dynamics is nothing if not extraordinary. The bar for confirmation must be set high, not to stifle imagination, but to protect our conclusions from error as we prepare to analyze 3I Atlas's orbit in detail. The stakes of this investigation become clear. If we find no meaningful connection between it and the comet swarm, that too is a valuable result. It would reinforce our understanding of these events as independent, driven by their own natural cycles. But if we find evidence of correlation that exceeds random chance, we may be on the verge of a paradigm-shifting discovery about how the solar system interacts with the greater galactic environment. Either outcome will deepen our understanding of the universe. The cosmos is not short of genuine mysteries, and it does not require us to invent additional ones. The key is to remain vigilant, open to surprising evidence, but anchored in disciplined methodology. The stranger from the stars has arrived, and its story is written in the geometry of its path, the chemistry of its ices, and the faint glow of its coma. It has traveled farther than we can truly comprehend to bring us a message, not of threat, but of opportunity. If we are careful, curious, and patient, we will decipher that message and add another chapter to humanity's ongoing attempt to understand its place in the universe. And so, with instruments ready and hypotheses in hand, we turn to the next step in our investigation. Part 7 begins, Orbit of Intrigue. The trajectory of 3I Atlas reads like a cosmic passport, a record of a journey that began far beyond the influence of our sun and will ultimately end there as well. Unlike the elliptical orbits that keep planets and comets locked in endless cycles around the solar system, this visitor follows a hyperbolic path, the unmistakable signature of an object traveling fast enough to break free of our sun's gravitational pull forever. Its course is a one-way slingshot, a dive from the deep reaches of interstellar space, a sharp curve around our star, and then an acceleration back into the darkness, never to return. There are no second chances here, no repeat flybys. 3I Atlas gets only one pass through our celestial neighborhood, and we have the rare privilege of observing it in real time. Its orbital elements tell a fascinating story about both its origin and its destination. 3I Atlas approaches from a direction roughly aligned with the constellation Perseus, though interstellar space offers no signposts to mark a precise point of departure. What we can measure is its hyperbolic excess velocity, the speed it will still carry even after escaping solar gravity. This velocity implies a journey that has lasted hundreds of thousands, perhaps millions of years, beginning in one of the nearest star systems and culminating here in our sky, at this very moment. One of the most intriguing aspects of this trajectory is its inclination relative to the ecliptic plane. The flat, disc-shaped region where most planets, asteroids, and comets reside. Rather than plunging in steeply from high above or below the planetary plane, 3I Atlas approaches at a relatively modest angle. This near-ecliptic geometry means that as it sweeps through the solar system, it passes through the general region of space where our 7-comet swarm is currently traveling. This inclination matters because it affects the probability of gravitational interactions. A visitor arriving from far above or below the ecliptic would whip through the solar system quickly, with little chance of influencing local objects. By contrast, 3I Atlas's path keeps it within the general orbital neighborhood of planets and comets for a longer period. That does not mean close encounters are taking place. The distances involved remain measured in hundreds of millions of kilometers, far beyond the range of significant gravitational perturbations. But it does create a window of time in which any potential interactions, however subtle, might occur. Adding to the complexity is the retrograde nature of its motion. While nearly every object native to the solar system travels around the Sun in the same direction, 3I Atlas approaches from the opposite direction, effectively swimming upstream through the current of the solar system. This retrograde motion produces extremely high relative velocities whenever it passes near other objects. Ironically, this tends to minimize gravitational effects rather than enhance them. Fast-moving objects spend less time within each other's spheres of influence, making any gravitational tug fleeting and weak. If 3I Atlas were somehow shaping the behavior of our 7-comet swarm, that influence would have to operate through a mechanism other than prolonged gravitational shepherding. These orbital characteristics establish an important framework for our investigation. They effectively rule out scenarios that depend on close, slow interactions between the interstellar object and local comets. Instead, any potential influence would have to be either indirect or operate through forces that act over large distances, perhaps electromagnetic effects, or some entirely new mechanism not yet described in classical celestial mechanics. One particularly significant part of this investigation involves 3I Atlas's orbital nodes, the points where its trajectory crosses the ecliptic plane. These crossings mark the times when the interstellar visitor comes closest to the regions where comets spend most of their time. If any kind of interaction is taking place, the nodes provide the most likely windows for it to occur. Fortunately, these points can be calculated with exquisite precision. Astronomers can determine the exact dates when 3I Atlas will cross the ecliptic, allowing us to monitor the 7-comet swarm for corresponding changes, unexpected brightness outbursts, tail disconnection events, or orbital perturbations that might hint at a shared influence. The challenge, however, is defining what truly counts as unusual comet behavior. Comets are notoriously unpredictable. Their brightness can fluctuate dramatically, their tails can fragment or shift direction, and their orbits can be altered by jets of outgassing material. These phenomena occur naturally as part of the normal life cycle of a comet interacting with solar radiation and wind. For any correlation to be meaningful, it must exceed the background level of ordinary cometary variability. Here is where rigorous statistical analysis becomes our most powerful tool. By continuously monitoring each of the 7 comets and cataloging every significant event, changes in brightness, tail morphology, or other notable activity, we can build a comprehensive data set. From there, we can test whether these events occur disproportionately near 3I Atlas's nodal crossings or perihelion passage. If the distribution is truly random, as the null hypothesis predicts, events should be scattered evenly across time. But if they cluster around key moments in 3I Atlas's orbit, the probability of such clustering happening by chance becomes vanishingly small. Even then, we must remain vigilant against the trap of selection bias, the tendency to focus on the events that support our suspicions while overlooking those that contradict them. A disciplined investigation demands that we document all relevant events, even those that fail to align with our expectations. Only by considering the full data set can we be confident that any correlation we find is genuine and not the result of cherry-picking evidence. The orbital evolution of 3I Atlas as it approaches perihelion also offers a crucial test. As it nears the Sun, solar heating should increase its outgassing activity, potentially producing more dramatic changes in brightness or tail structure. If some hidden mechanism links 3I Atlas to the 7-comet swarm, we might see corresponding spikes in activity across multiple comets near the same time. The timing of these events will be critical. A synchronized response across objects separated by millions of kilometers would be difficult to explain as coincidence. In this way, 3 Atlas's orbit provides both the challenge and the opportunity for discovery. The geometry of its path sets strict limits on what kinds of interactions are physically possible, yet it also gives us a precise observational schedule, moments when we should be paying closest attention. This is where careful science meets cosmic detective work. The next phase of our investigation will focus on refining these orbital calculations, predicting future key dates, and coordinating observation campaigns to ensure we do not miss any potential signs of connection. The cosmos rarely offers such a well-timed experiment. If there is a hidden relationship between this interstellar traveler and the comets of our solar system, the evidence will be written into the timing and geometry of their motions. It is up to us to read that story correctly. The predicted brightness curve for 3I Atlas suggests a steady, almost rhythmic increase in luminosity as it continues its dive toward the sun. Each increment of brightness, each flare, and every surge in activity is a page in the story of this interstellar traveler. While we expect a gradual brightening overall, nature is rarely perfectly smooth. Sudden outbursts may punctuate the curve if volatile materials deep within the object begin to vaporize rapidly, or if internal stresses become too great and trigger fragmentation events. These disruptions are not random chaos. They occur at predictable times and locations along the comet's orbital path, governed by physics and chemistry that we can model with remarkable precision. If the so-called 7-comet swarm in our solar system is somehow reacting to 3I Atlas, if there is truly a connection between these bodies, then their responses should correlate closely with these predicted brightening events. The tighter and more precise the temporal correlation, the stronger the case for a genuine link rather than mere coincidence. Yet, as always in science, we must also consider more conservative explanations. What if these correlations are not the result of direct communication between objects, but rather shared responses to common external forces? Space weather offers a compelling alternative hypothesis. Variations in solar activity, fluctuations in the interplanetary magnetic field, or the passage of high-speed particle streams could potentially affect all comets in the inner solar system simultaneously. These influences might create the appearance of coordination without requiring any exotic mechanism of interstellar communication. This solar influence model makes a clear, testable prediction. If the behaviors of 3I Atlas and the 7 comets are linked, we should be able to trace those links to specific solar triggers: a coronal mass ejection, a solar flare, a shock wave propagating through the solar wind, events we can observe, time, and map with existing instrumentation. The presence of such triggers would argue strongly for conventional astrophysics rather than anything extraordinary. The orbital path of 3I Atlas also places strict limits on how long any influence can persist. Its hyperbolic trajectory ensures that its visit is fleeting by cosmic standards, perhaps 18 months from first detection to final disappearance into the dark. This short window means that any effects on the comet swarm must be rapid, measurable, and observable with today's technology. Slow, cumulative processes playing out over decades or centuries would simply remain hidden during this brief encounter. As we focus on the upcoming perihelion, we are reminded that celestial mechanics operates with clockwork precision. Gravity does not care for human speculation. The orbit is what it is. 3I Atlas will reach its closest approach to the Sun at a time and place dictated by mathematics alone. What remains unknown is whether that moment will also mark the unveiling of a deeper story, one that ties this interstellar visitor to the other mysterious objects in our solar system. Perihelion, the point of closest approach to the Sun, represents the moment of truth for any comet. Months or even years of slow approach suddenly culminate in a spectacular crescendo of activity as the object plunges through the region of most intense solar radiation. For 3I Atlas, this milestone carries unique significance, as it marks the first time this alien traveler will experience the full power of our star. The physics of perihelion are both predictable and dramatic. As the comet draws closer, solar radiation increases following the inverse square law. Each halving of the distance doubles the energy delivered. Ice that has remained stable throughout the object's eons-long interstellar journey suddenly vaporizes, producing a glowing coma and a brilliant tail. This is the moment when a dark, nearly invisible fragment of another star system becomes a blazing beacon in our sky. But this is not just any comet. Its composition is likely very different from the icy bodies we know so well. Formed in the distant reaches of another solar system, its chemistry may favor exotic molecules, carbon monoxide, methane, carbon dioxide, perhaps even more complex organics, frozen in ratios that differ dramatically from those seen in Oort cloud comets. During perihelion, these compositional fingerprints will be revealed through spectroscopic analysis. Each molecule emits light at characteristic wavelengths when excited by solar radiation, allowing astronomers to piece together a chemical portrait of this alien object. That spectrum will be more than just data. It will be a preserved snapshot of another star's outer disk, a relic from the formation era of a distant world, delivered across light years of space for us to study. If there is indeed a connection between 3I Atlas and the 7-comet swarm, perihelion is the likeliest time for that connection to manifest. The intense solar energy might trigger whatever mechanism drives coordination, if any exists at all. Astronomers will be watching for a number of key indicators. Sudden brightness increases, for instance, often mark the exposure of fresh ice or the rapid release of volatile gases. These outbursts can cause a comet's luminosity to increase by a factor of 10 or more in a matter of hours. Not only are these events visually stunning, they also provide valuable clues about internal structure and composition. Another critical observation involves jets of material streaming from specific regions on the comet's nucleus. These can act like tiny thrusters, imparting measurable non-gravitational forces that subtly alter the comet's trajectory. We've seen such effects in many solar system comets, but detecting them in an interstellar object would provide an unprecedented glimpse into how alien materials respond to solar heating. The tail system of 3I Atlas will be another rich source of data. Ion tails, created when ultraviolet sunlight ionizes gas molecules, are shaped and directed by the solar magnetic field, forming long, straight streamers that always point away from the sun. By monitoring their shape, length, and reaction to solar wind variations, scientists can learn how gases from another stellar nursery behave in our own star's domain. Any peculiarities compared to ordinary comets could point to compositional or structural differences unique to interstellar chemistry. Dust tails tell a different story. Rather than being governed by magnetic fields, they are sculpted by radiation pressure. The size distribution of dust particles determines how strongly they are pushed away from the sun. Fine particles can be swept into dramatic sweeping arcs, while larger chunks follow nearly ballistic trajectories. If 3I Atlas produces an unusually brilliant or extended dust tail, it might indicate a composition rich in fine-grained material, or perhaps a catastrophic fragmentation event that suddenly releases a vast quantity of dust into space. Indeed, fragmentation represents the most dramatic possible outcome of perihelion passage. A comet is a fragile body, often little more than a loosely bound rubble pile. The combination of intense heating, rotational stress, and internal pressure from vaporizing volatiles can tear it apart. When this happens, the object can split into multiple pieces that continue along the same orbital path, but gradually separate over time. Should 3I Atlas fragment, it would be a bittersweet event for astronomers. On one hand, it would expose pristine interior material, offering a once-in-a-lifetime chance to study matter that has remained unchanged since its birth. On the other hand, it could complicate any search for correlations with other comets, as the new fragments would need to be tracked and their trajectories disentangled from one another. The environment near perihelion will not be quiet. The sun is approaching solar maximum, meaning increased flare activity, stronger magnetic fields, and frequent coronal mass ejections. These conditions can produce spectacular visual effects, including tail disconnections, kinks, and plasma instabilities that make a comet appear to twist and writhe in real time. Each event will need to be carefully analyzed to determine whether it is simply a natural response to solar wind, variations, or evidence of something more exotic. Distinguishing genuine coordination from coincidental simultaneity will require precision, timing, and detailed modeling. Solar wind disturbances travel outward from the sun at measurable speeds. If an outburst on 3I Atlas and a corresponding event in the 7-comet swarm occur at the same time but cannot be explained by solar wind propagation, that will strengthen the case for a direct connection. This is why astronomers, both professional and amateur, are mobilizing like never before. Citizen scientists across the globe are preparing their telescopes to capture continuous light curves, images of tail evolution, and real-time alerts for any outbursts or fragmentation events. Professional observatories, space-based instruments, and comet hunting surveys will coordinate to ensure that no significant development goes unrecorded. Together, this network will create the most comprehensive observational campaign ever mounted for an interstellar object. In the end, perihelion is not just an astronomical event. It is a moment of discovery, a chance to glimpse the heart of an object that has traveled unthinkable distances to reach us. Whether 3I Atlas passes quietly through the inner solar system, or whether it delivers dramatic surprises that rewrite our understanding of interstellar visitors, one thing is certain: this fleeting encounter will leave us with data, insights, and perhaps even more questions about our place in the cosmos. Every photon we collect from 3I Atlas is not just light. It is an irreplaceable data point, a time capsule of conditions that existed in another star system long before humanity ever looked to the sky. Each observation carries scientific weight, preserving information that may never be available again once this interstellar traveler disappears into the darkness. But to fully understand its story, our investigation must go beyond simply tracking this lone visitor. We must monitor the entire cast of characters, all 7 of the major comets already present in our solar system, and watch for behavioral anomalies that may line up with 3I Atlas's key events. This comparative approach is the only way to separate ordinary comet variability from significant correlations that could hint at deeper connections. Detecting such correlations is no small task. It requires extraordinary precision, pushing the limits of our current observational technology. Minute changes in brightness, subtle asymmetries in comet tails, and tiny orbital perturbations may be the only clues we receive. Faint signatures that could suggest interactions too subtle for conventional detection methods. The work is painstaking, but the stakes are high. Any genuine link between these comets and our interstellar visitor could point to a process that challenges our understanding of cometary dynamics. As perihelion approaches, we are reminded that the universe operates under laws that do not bend for human curiosity. 3I Atlas will do what physics dictates. It will brighten, form a coma and tail, perhaps shed material or fragment, all in response to the unyielding force of solar heating. It does not exist to put on a show for us. And yet, within those natural, predictable processes lie opportunities for profound discovery. Insights into the chemistry of interstellar material, the structural integrity of alien ices, and possibly, if we are fortunate, the detection of correlations with our local cometary population that hint at something extraordinary. Whether such revelations occur is a question that can only be answered by careful, disciplined observation. Part 9. The Swarm and the Sun, our Sun. The great engine at the heart of the solar system is no constant beacon. It breathes in cycles, oscillating between calm and fury in a rhythm as regular as a cosmic heartbeat. The 11-year solar cycle that governs this behavior is reaching its peak in 2025. We are entering solar maximum, a period when the sun becomes more restless and dynamic, when sunspots bloom across its surface like magnetic scars, and when vast amounts of energy are stored in its twisted magnetic fields. These fields sometimes snap, releasing their pent-up energy in violent outbursts. Coronal mass ejections, billion-ton clouds of charged plasma, are hurled into space, traveling at speeds that can reach millions of kilometers per hour. Solar flares release bursts of radiation that can cross the solar system in mere minutes. Together, these events transform our normally placid star into a stormy, unpredictable force. For our investigation, this increased activity is both a blessing and a challenge. Solar maximum amplifies cometary behavior. Denser particle streams and stronger magnetic fields make even modest comets appear more dramatic. Ion tails grow brighter and longer, their structure becoming more complex under the influence of fluctuating solar winds. Consider what happens when a coronal mass ejection slams into a comet's tail. The magnetic shock can compress or twist the tail, sometimes even snapping it off entirely in a phenomenon known as a tail disconnection event. Within hours, a new tail begins to form in the restructured magnetic field, leaving the old one adrift in space like a ghostly ribbon. To the untrained eye, these events can look supernatural, Tails kink, twist, or ripple in ways that seem to defy simple gas dynamics. A tail might appear to break apart as though struck by an unseen weapon. But these are not attacks. They are natural responses to a changing magnetic environment. The comet's nucleus remains unaffected. Only its fragile stream of ionized gas is reshaped by the forces of space weather. The visual impact, however, can be so dramatic that even experienced observers may be tempted to reach for exotic explanations. This is where disciplined science becomes crucial. Every object in our study, the 7 traditional comets and 3I Atlas, shares the same solar environment. They are all bathed in the same solar wind, exposed to the same flares, and buffeted by the same shock waves from coronal mass ejections. If we see multiple comets exhibit tail disruptions at the same time, the most logical explanation is not mysterious communication between them, but a shared response to a single solar trigger. A powerful storm can create the illusion of synchronization across the entire inner solar system. The effects of solar maximum are not limited to comets. Earth's own magnetosphere is deeply affected by these energetic events. When solar particle streams collide with our planet's magnetic field, they compress it, inducing electric currents that can flow through power lines and transformers. In extreme cases, this can trigger large-scale blackouts, as happened during the March 1989 geomagnetic storm that temporarily shut down Quebec's electrical grid. Satellites, too, are vulnerable. High-energy particles can penetrate shielding, scramble electronics, or cause temporary communication blackouts. GPS navigation becomes less accurate, and data links with spacecraft can fail without warning. Even commercial aviation must adapt to the sun's mood swings. During strong geomagnetic storms, airlines reroute polar flights to lower latitudes to reduce the radiation exposure of passengers and crew, and protect aircraft systems from electromagnetic interference. And then there is the sky show. Auroras intensify, spilling far from their usual polar haunts into mid-latitudes. To the casual observer, the coincidence of brilliant auroras, active comets, and technological disruptions can feel uncanny, as if all of nature were conspiring to send a message. But here again, we must separate appearance from reality. The same solar storm that brightens comet tails and produces auroras is also responsible for the disruptions we feel on Earth. Comets are not the cause of geomagnetic disturbances. They are simply fellow participants in the great drama of solar activity. This distinction becomes even more important when evaluating claims about 3I Atlas. If satellites fail or power grids falter during its perihelion passage, the temptation to connect these events to the interstellar visitor will be strong. Yet the physics tells a simpler story. The sun drives these phenomena. The timing of 3I Atlas's arrival during solar maximum is fascinating, but it is not necessarily meaningful beyond coincidence, unless careful analysis shows otherwise. That analysis requires rigor. Historical records of comet discoveries combined with solar activity data spanning multiple cycles could reveal whether active solar periods coincide with enhanced cometary arrivals. If such a pattern exists, it might suggest that gravitational or electromagnetic effects of solar maximum subtly influence the dynamics of comets at the edge of the solar system, nudging more of them inward. This is an open question, one that invites careful statistical study rather than speculation. Our methodology must remain clear and disciplined. Whenever unusual comet behavior is observed, the first step is to consult space weather data. Was there a flare? A coronal mass ejection? A high-speed solar wind stream? Only after ruling out these known drivers should we seriously consider the possibility of exotic interactions or inter-object coordination. This prevents us from leaping to extraordinary conclusions when ordinary explanations suffice. Fortunately, our monitoring infrastructure has never been better. Space-based platforms such as SOHO, the Solar and Heliospheric Observatory, and the Solar Dynamics Observatory, along with networks of ground-based magnetometers, provide continuous real-time coverage of solar conditions. This constant stream of data allows scientists to predict the arrival of solar storms and compare their timing with observed cometary events with remarkable precision. If 3I Atlas influences other comets in a way that cannot be explained by solar activity, those effects should stand out above the noise of ordinary variability. Amateur astronomers are vital partners in this work. Around the globe, dedicated observers use backyard telescopes and digital cameras to capture comet brightness curves, tail structures, and fragmentation events with astonishing fidelity. Their contributions often exceed the temporal resolution possible with oversubscribed professional observatories. Together, professionals and amateurs form a worldwide distributed sensor network, collecting data that can be analyzed for correlations on timescales as short as minutes. This abundance of data will be essential in the coming months. The heightened solar activity of 2025 will produce a constant background of space weather events that will both enhance comet visibility and complicate efforts to isolate subtle, non-solar effects. The challenge lies in applying strict evidentiary standards, demanding that any claimed correlation exceed what we would expect by chance or by shared solar triggers, while remaining open to the possibility that something genuinely new and unexpected may be unfolding. The cosmos has a way of surprising us. Subtle connections, once dismissed as impossible, have later been revealed as fundamental truths of nature. As we continue to monitor 3I Atlas, the 7-comet swarm, and the Sun itself, we are watching a dance choreographed by magnetic fields and particle streams that link every object under the Sun's domain. Somewhere within that choreography, perhaps, are steps we have not yet recognized, patterns that could hint at new physics or previously unseen relationships between the solar system and the wider galaxy. Part 10. Echoes on Earth. The influence of space weather does not stop at the edge of space. It reaches down to Earth, touching the infrastructure of our technological civilization in ways most people never think about until something goes wrong. Comets themselves pose no threat to Earth, but the solar storms that make their tails so spectacular can wreak havoc on the systems we rely on daily. Geomagnetic storms can induce powerful currents in electrical grids, overheating transformers and triggering cascading blackouts. The blackout in Quebec in 1989 remains one of the most dramatic reminders of this vulnerability. Satellites are even more exposed. High-energy particles from solar storms can disable instruments, scramble data, and in some cases cause permanent damage. Weather monitoring, communications, and GPS systems are all more error-prone during solar storms. Commercial aviation is not immune either. Flights over polar routes are diverted during periods of high activity to minimize radiation exposure and protect avionics. Systems. The overlap between comet activity and solar maximum creates a perfect storm of perception. To the public, it may appear as though the comets themselves are somehow triggering these events. After all, the timing is dramatic. But the true cause lies with the Sun, which drives both the spectacular sky displays and the disruptions to human systems. It is essential to resist the temptation to attribute causality where none exists. As 3I Atlas approaches perihelion, we must maintain this clarity. If a satellite fails, if GPS becomes unreliable, or if power grids flicker during the same week that the comet brightens, solar activity remains the first and most likely suspect. The temptation to weave these events into a narrative of cosmic significance must give way to disciplined analysis based on evidence and physics. The coming months will test our ability to separate coincidence from causation, noise from signal, but they will also give us a rare chance to witness the Sun, comets, and Earth interacting in a cosmic drama that is as real as it is beautiful. A reminder that we live in a dynamic, interconnected system where even the smallest visitor from another star can become part of the story. Government agencies responsible for monitoring space weather have built some of the most advanced early warning systems ever developed, designed to protect our increasingly technology-dependent civilization. These systems track solar storms from the moment they are born in powerful solar flares, follow their journey across interplanetary space, and predict their eventual impact on Earth's magnetosphere. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center, for example, issues alerts and forecasts with a level of urgency comparable to warnings for hurricanes, tornadoes, or other severe terrestrial weather events. This coordinated monitoring effort is crucial because it allows scientists and engineers to compare the timing of space weather events with any technological problems that arise, including those that might coincide with periods of unusual comet activity. If infrastructure failures occur during a documented geomagnetic storm, the likelihood that solar activity is the culprit is far higher than any mysterious influence from a distant comet such as 3I Atlas. The active solar conditions expected in 2025, during the peak of the solar cycle, guarantee frequent opportunities for such comparisons. Solar maximum produces multiple geomagnetic storms each month, meaning that the overlap between infrastructure failures and comet observations will sometimes happen purely by coincidence, even when there is no real causal connection between them. In fact, the statistical expectation is that some correlations will always occur by chance in a busy and interconnected system like Earth's technological network. Amateur radio operators offer a fascinating additional layer to this monitoring network. Their hobby often makes them the first to notice space weather effects, sometimes even before official government systems release alerts. Radio wave propagation through Earth's ionosphere is extremely sensitive to disturbances caused by solar storms. During strong geomagnetic events, experienced operators can immediately tell that something has changed. Signals that normally travel reliably may suddenly fade out, or strange long-distance skip patterns may appear. This global distributed network of enthusiasts essentially acts as a real-time sensor grid, providing rapid confirmation that solar activity is affecting our planet. If 3I Atlas, or any interstellar object, were to somehow influence Earth's electromagnetic environment, we would expect to see measurable anomalies across many different independent systems. That is precisely why a strong investigative framework is required, to ensure that scientists don't fall into the trap of attributing unrelated phenomena to a single dramatic cause. Human psychology naturally favors linking events that occur close together in time, especially when those events are unusual or attention-grabbing. The rarer or more dramatic the events, the stronger our instinct becomes to treat their coincidence as meaningful rather than random. But statistics teaches us that even in a purely random sequence, clusters and patterns will appear eventually. A classic example is flipping a coin. If you flip it thousands of times, you will inevitably encounter seemingly impossible streaks, 5, 6, even 10 heads in a row, purely by chance. Similarly, when solar storms, comet outbursts, and technological glitches all occur within the same week, it feels significant, but it may still be nothing more than coincidence. The challenge for researchers is to develop objective criteria that separate meaningful correlations from random clustering. This is where modern statistical tools become indispensable. Professional space weather research relies on techniques like superposed epoch analysis, which examines data centered around key events to detect consistent patterns and cross-correlation functions, which measure how strongly two different data sets are related over time. These approaches also address the multiple comparisons problem, which arises when scientists test many possible correlations at once. The more comparisons you make, the more likely you are to find a seemingly significant pattern by pure chance. By applying rigorous statistical methods, researchers can avoid false positives while still remaining sensitive enough to detect genuine signals if they exist. Maintaining high standards of evidence is essential, particularly in an era when a single unexplained blackout or system failure can spark viral speculation about cosmic influences. The global scope of modern infrastructure provides countless opportunities for spurious correlations. With thousands of satellites in orbit, billions of connected electronic devices, and vast power and communications networks operating continuously, minor failures occur every day for completely mundane reasons: equipment aging, software errors, weather-related damage, or scheduled maintenance. But when those failures happen to coincide with a period of heightened comet activity or a rare interstellar visitor like 3I Atlas, people are more likely to seek extraordinary explanations. Power outage that would normally be attributed to a transformer fault may suddenly be blamed on mysterious cosmic forces simply because it happened on the same day a bright green comet was in the sky. This is where public education and clear communication become crucial. The more the general population understands about the actual mechanisms by which solar activity affects Earth, geomagnetically induced currents, radiation storms, satellite drag, and so forth, the less likely they are to leap to exotic conclusions when something goes wrong. Education is not just for the public. It is a central part of the scientific process itself. The teams investigating potential links between 3I Atlas and the 7-comet swarm must be meticulous about distinguishing between what is well established and what is purely hypothetical. There is nothing wrong with exploring exotic hypotheses. Indeed, that is part of the excitement of frontier science, but researchers must avoid presenting speculation as fact. By keeping a clear separation between confirmed cause and effect relationships and intriguing but unproven possibilities, the scientific community can remain open to discovery without fueling misinformation. Our modern civilization, for all its fragility, also offers unprecedented opportunities for discovery. The same interconnected technological web that is vulnerable to solar storms also produces vast streams of data, allowing scientists to measure electromagnetic phenomena with extraordinary sensitivity. Instruments aboard satellites, ground-based magnetometer arrays, and even consumer electronics can register subtle fluctuations that would have been invisible to earlier generations of scientists. This heightened sensitivity could allow us to detect very faint signals, small deviations from the norm that might hint at processes we don't yet fully understand. Perhaps there are interactions between interstellar objects and the solar wind that we have not yet characterized. Or perhaps some apparent anomalies will turn out to be nothing more than statistical noise once we gather enough data. Either way, the key is patient, systematic observation. By combining professional monitoring systems, distributed networks of amateur observers, and robust statistical analysis, we have the best chance ever of answering the question at the heart of this investigation. Is 3I Atlas simply a passive traveler obeying the natural laws of physics? Or does its passage through our solar system reveal something new about the way cosmic forces interact? Only by resisting the temptation to jump to conclusions can we be sure that, when we do find something truly extraordinary, we will recognize it for what it really is. The more carefully we study celestial events, the more we must guard against one of the greatest traps in human reasoning: the tendency to mistake coincidence for causation. Every new observation, every coincidence of timing between comet outbursts, solar storms, and technological disturbances provides fertile ground for misinterpretation. As we prepare to examine how human psychology and cultural narratives shape our perception of the cosmos, we must first remember that the universe operates according to physical laws that do not bend to our desires. Our hopes for profound history-making discoveries do not influence orbital mechanics, magnetic fields, or solar cycles. Earth's response to space weather follows well-understood mechanisms that scientists have measured and modeled for decades. Even during periods of intense cometary activity, the echoes of solar storms reverberate through Earth's technological systems in ways that are measurable, predictable, and consistent with established physics. Electrical grids experience induced currents. Satellites face increased drag. GPS signals shift as the ionosphere becomes disturbed. None of these require exotic explanations, and yet within the background noise of normal space weather, faint signals may lurk, subtle patterns that could reveal new interactions, if only our instruments are sensitive enough to distinguish correlation from true causation. Our investigation remains firmly grounded in physics, but it must stay alert to possibilities that might challenge conventional models and force us to reconsider the way celestial and terrestrial events are linked across cosmic scales. Throughout history, comets have been treated as cosmic messengers, their sudden appearances interpreted as warnings, omens, or heralds of great change. The simultaneous arrival of multiple comets has always carried a special weight in human imagination. Such clustering taps into deep psychological patterns that transform objective astronomical events into subjective narratives. Ancient Chinese astronomers kept meticulous records of cometary appearances, correlating them with dynastic change, natural disasters, and periods of social upheaval. They referred to comets as broom stars, sweeping away the old order to make room for the new. This metaphor reveals humanity's ancient instinct to assign meaning to celestial timing. In medieval Europe, chroniclers took a similar approach, framing comets as divine warnings of disaster or transformation. The Great Comet of 1066, which appeared shortly before the Norman conquest of England, became permanently associated with the fall of the Saxons and the rise of a new era. Whether the comet influenced the outcome or simply provided a convenient symbol hardly matters now. The connection embedded itself in cultural memory. The 1758 return of Halley's Comet coincided with the 7 Years' War, a conflict that redrew the political map across 3 continents. Colonial American observers saw the comet as an omen of revolution and independence, while European astronomers celebrated its return as a triumphant confirmation of Newton's gravitational predictions. These examples show how the same celestial event can be woven into very different narratives depending on cultural context and political needs. The human brain is a pattern-seeking engine, wired to connect clustered, unusual events into meaningful stories. Wars, plagues, disasters, and comets, when they appear together, are rarely treated as separate coincidences. Instead, we interpret them as connected threads of a grand design, a cosmic plot unfolding with humanity as its audience. This psychological tendency becomes even more pronounced during times of social tension or uncertainty. When populations are already searching for signs of change because of political instability, climate anxiety, or technological disruption, they are especially primed to interpret celestial events as harbingers of transformation. The comet swarm of 2025 arrives at precisely such a moment, during an era defined by rapid global change and geopolitical tension. This makes it fertile ground for narratives that blend astronomy with prophecy, science with speculation. Modern media supercharges this effect. Social media algorithms amplify content that is dramatic, emotional, and visually compelling, often at the expense of nuance and accuracy. Dramatic comet images spread rapidly, accompanied by speculative claims, doomsday theories, and mystical interpretations. Amateurs with video editing software can produce slick, professional-looking content that pairs real comet imagery with ominous soundtracks and suggestive narration, framing these events as evidence of alien visitation or impending apocalypse. The democratization of content creation has created a distributed, collaborative myth-making machine. Multiple independent creators frequently converge on similar themes without any formal coordination, giving the illusion of consensus around ideas that may have no scientific basis. In this way, a straightforward astronomical observation, 7 bright comets in a single year, can evolve into an elaborate, crowdsourced narrative about cosmic warnings, alien fleets, or divine messages. Each retelling adds new details, speculation, and emotional framing, pushing the story further from verifiable fact and closer to collective myth.